Hello and welcome to this lecture on advanced electric drives. In this lecture, we will try to discuss something on utility friendly AC drives. What do we mean by utility friendly? Utility is the AC grid that is available to us. The AC grid could be a single phase grid or it could be a three phase grid. Now, when we have the AC supply that is available to us in the form of a three phase or a single phase grid, and ultimately we are trying to control an AC motor, what are the various possibilities that we have? So, let us try to list the possibility of controlling an AC drive which requires variable voltage and variable frequency when we have a fixed voltage and fixed frequency grid available to us. So, we have the following possibilities. So, conventional AC motor drive So, what are the various possibilities we have when we talk about the conventional AC motor drives? We want to have a variable voltage and a variable frequency output, and the available power supply is an AC voltage. So, we can have first an uncontrolled converter, uncontrolled AC to DC converter, followed by a DC to AC inverter. Now, this is the first possibility, that the first stage, we have two stages in this case. We have the AC power supply available to us, we can convert that to the DC by means of uncontrolled converter. And when we talk about uncontrolled converter, we usually talk about the diode bridge rectifier. So, the first stage is basically a diode bridge. So, this is a diode bridge that we have here. So, this is a diode bridge and plus inverter. So, if we see the schematic diagram here, we have the diode bridge first and then we have an inverter. The inverter could be made up of IGBTs or GTOs for high power, and here we have a DC link. And the input in this case could be a single phase or a three phase AC grid. When we have low power application, say for example, if the drive is for low power application which is below, let us say 10 kilowatt, we can go for single phase bridge. So, in the input side, what we have here is the three phase AC supply, then we have the AC to DC converter, this is uncontrolled, and then we have the motor which is connected at the output, and this is the AC motor, and this is the DC to AC inverter. So, this is one of the configuration. We are converting AC to DC, the DC to variable voltage and variable frequency AC. Now, in this case, if we see in the front end, we have a diode bridge. This is called a front end converter. Front end converter. So, this uncontrolled rectifier or uncontrolled converter is called a front end converter also, because it is coming at the front end of the drive system. When we talk about the drive, we have a AC supply that is available to us. Ultimately, we have to control the motor, which is an AC motor, and in the input side we have a AC to DC converter, that is the front end converter. Now, when we interface with the grid or utility, the utility will be supplying the current to the front end converter. Now, this current, in case of a diode bridge rectifier, will be full with harmonics. In fact, if we see a 6 pulse bridge rectifier and see the input current will be full with harmonics, and hence the harmonics will be drawn from the power system, which is going to deteriorate the condition of the power systems, and hence the power quality will go down. So, the input current here, the input current will contain harmonics which will pollute the power system. And result in poor power quality. So, this input current here, if we try to see the input current of a typical 6 pulse diode bridge rectifier, we will see that the input current contains harmonics, and harmonics will be of this nature. We have the input current here. So, this will have something like this structure, where the current is like this. This is the current, and the voltage will be sinusoidal. This is the V, the voltage, and we have the current. Now, current contains harmonics, and hence this drive, although we are able to control the drive through the inverter, this drive will have detrimental effect on the power system. So, this is not a utility friendly drive. Now, what is the other possibility? Other possibility is to have a control rectifier. That is also the conventional topology, in which the front end converter is a control rectifier. So, we can have another possibility. So, the other possibility is that we can have control converter plus this is a AC to DC converter plus a DC to AC inverter. So, we can have the structure like this. We can have, usually we use a SCR bridge here. We have a SCR bridge in this case. We have a 3-phase supply, and in this case, when we have variable input voltage, we usually have a current source inverter. So, here in this case we can have IGBTs or GTOs or even SCRs. So, we saw that by means of a GTO here, the front end is a control converter, and after that we have a inverter. This is called a current source inverter. and this is a DC to AC conversion, and the front end is a DC to DC AC to DC conversion, and we have the motor. The motor is fed from this inverter. So, we have AC motor. Now, in this topology also, if we see, the front end is a SCR control rectifier having thyristors. In the front end also we will have harmonics. When we delay the triggering angle, in this case the phase angle will also change. So, in this case the situation is little different from the uncontrolled rectifier. Here not only we will have harmonics, we also have poor power factor, in the sense that we have a delay in the current, and hence the phase angle of the current will be lagging the voltage, and hence we have both harmonics and reactive power. So, this is also not utility friendly. We are injecting the harmonic current into the power systems, and hence the power quality is deteriorated. So, here the input current in this case contains harmonics, and it lags behind the supply voltage for a finite triggering angle alpha. So, this kind of topology where we have a current source inverter feeding a AC motor is also not utility friendly. Although we are able to control the motor, we are not able to have a system where the power system is going to be more free from harmonics. The power system in this case will contain harmonics, and harmonics will bring down the power quality. Now, what is the other possibility? Other possibility which is conventionally employed is a cycloconverter. In a cycloconverter, what we do, we feed the motor from AC to AC cycloconverter. It is AC to AC conversion, but again in the input side we have harmonics. The third possibility we have in this case is a cycloconverter, AC to AC cycloconverter. So, in this case what we have here, we have the cycloconverter, and the cycloconverter is shown by means of a dual converter block like this, and the input in this case is a AC power supply, 3-phase AC, and the output here is the AC motor, and what we have here is 3-phase to 3-phase cycloconverter. So, primarily it is a AC to AC conversion. In fact, what we do here is that from a fixed AC, the input power supply is usually an infinite bus. The input voltage and the frequency are constant. So, what we do here is that by having a cycloconverter, we can generate variable voltage and variable frequency from a fixed voltage and fixed frequency. But in this case also the input current will have harmonics. So, all these three possibilities that we have for controlling AC drives are not utility friendly. So, what is the solution? The solution is to have a topology in which the input current will not have any harmonics, and we will only draw active power from the utility. So, the criteria of having a utility friendly drive are as follows. Number 1, the input current should not have any harmonics, and the input current should be in phase with the input voltage. So, we will be talking about a utility friendly drive AC drive, and the features of these drives are the input current drawn from the supply is sinusoidal, and the power factor, the input power factor is 1, which means only active power is drawn from the supply. So, if you try to analyze these 2 points, the first point says that the input current is sinusoidal. It means when we are controlling the motor from an inverter, the front end converter will only draw sinusoidal current, no harmonics, and when we do not draw any harmonics, the input is not polluted by harmonics, and hence the power quality is maintained. Number 2, that we are only drawing active power from the supply. It means the supply power factor is unity. The current is in phase with the voltage, and hence we are only drawing the active power, there is no reactive power, and when we are not drawing any reactive power, the efficiency is better, because the current, the effective current is reduced, because the reactive current component is 0, and associated losses with the reactive current is also 0. So, this is a drive which is the state of the art drive, in which we are not only taking care of the control of the AC motor, but also we are ensuring that the front end converter will maintain the power quality. Now, when we have this criteria, we can go for a practical drive. Now, we have seen various types of motors, induction motor, synchronous motors, and other special motors like Swiss reluctance motor, etc. Now, we will apply this to very popular induction motor, and we will have a configuration where we will have a utility friendly induction motor drive. Now, we are talking about 2 converters, converter 1 and converter 2. The converter 1 is interface with the supply, that is the front end converter. So, we have 2 converters here. We have converter 1, and then we have the converter 2, and in between we have the DC link, this is VD or VDC, and we have we have the motor, the induction motor we have IM stands for the induction motor, and then the front end converter is connected to the input supply. So, we have the input AC here, so these two converters are connected in cascade, and the first one is a AC to DC converter. So, we have here a AC to DC converter. This is called AC to DC front end converter, and then this is DC to AC load end converter, and this is typically an inverter. So, these two converters are joined by means of a DC link, and the DC link contains a capacitor, and the capacitor maintains that particular voltage at VDC. Now, the control of these two converters are somewhat independent of each other. The load end converter is controlled in a given control scheme, which could be a simple V by F control, it could be vector control, or it could be director control, to ensure good performance of the motor. So, the converter 2 will ensure good performance, ensures good performance of the induction motor. And we could do, so for example, it could be a simple V by F control, or it could be vector control, or it could be director control. So, the load end converter will control the motor. The responsibility of the load end converter is to control the motor with good performance. Now, what about the front end converter? The front end converter ensures the input current is sinusoidal and the input current power factor is unity. So, the front end converter is called a utility friendly converter. So, the job of the front end converter, this ensures sinusoidal input current at unity power factors. So, these two converters are controlled somewhat independently, and the front end converter ensures sinusoidal current at input power factor equal to 1, and the load end converter ensures good motor performance. Now, after this we will try to discuss about the detailed topology of these two converters, converter 1 and converter 2, with the control scheme for an induction motor drive. Now, these two converters, if you see the structure of these two converters, they are, let us say we have 3-phase power supply available to us. They are 3-phase converters made up of IGBTs or GTO. If we go for medium power applications, primarily these converters will be made up of IGBT, insulated gate bipolar transistors, and these are the voltage source converter structure. So, the front end converter is also a voltage source converter, the load end converter is also a voltage source converter. So, we will see the detailed topology of these two converters. So, we have the structure like this. The front end converter will have a structure in which we have six IGBTs. So, these are the gates of the IGBTs. The feedback diodes. And this converter is interfaced with the supply through three inductors. The inductor helps in control of current. So, when we want to control the input current free from harmonics and the input current should be in phase with the input voltage, we require these inductors essentially for current control. So, we have three inductors here for three phases. So, this is for phase A, phase B and phase C. Now, this is connected to the first phase, then we have the second phase and then we have the third phase. And this is connected to the AC supply, and we have the AC supply in this case, 3 phase AC, the grid is 3 phase here. So, we have the AC supply in this case which is available to us. And this is the neutral point N, and we can call this to be V A N. This is phase A, V B N, and this is V C N. Or more precisely, we can call it as V A S N, V B S N and V C S N. So, this is the source voltage. So, we can call it to be V A S N, B S N and C S N. A, B, C are the various phases, S is the source and N is the neutral. Similarly, here we have the converter here. So, we can call this as V A C N, V B C N and this is V C C N. C stands for the converter, and these two are linked by means of an inductor. The inductor is of the same value for phase A, phase B and phase C, and we can call this inductor as L. The value of the inductance is L and the reactance is omega L. So, it is j omega L here. So, the inductors, each value of the inductor is L and the reactance is j omega L. And this is connected to the DC link. The DC link comes in between. So, we have the DC link here which is having a capacitor and then we have the load end converter, and that is similar to the IGBT front end converter. We have a similar structure in the load end. So, we have the same structure here. We have an IGBT inverter here having 6 IGBTs. We have the third leg also here. These are the feedback diodes which will facilitate bidirectional current into the windings. The gate circuit, and this is the induction motor which is connected to the 3 phases of the load end converter. So, this voltage is a DC link voltage which we can call to be VDC, and when we see the power flow diagram here, the power is flowing from AC to the DC link to the motor. So, it is from the source to the load for motoring. So, for the motoring we can say that the power is flowing from the AC source to the load through the DC link. So, the flow of the power is like this. So, this is the flow of the power flow for motoring, and again this power is flowing to the motor. So, this is the flow of the power. So, here we have the DC link. Now, this converter, when we talk about the motor, the converters are voltage source converters. So, the DC link voltage has to be maintained constant, and unless we have a constant DC link voltage, it is very difficult to control the induction motor. So, the objective here is to keep VDC constant. So, the VDC can be kept constant by controlling the front end converter. So, the first objective in this case to keep VDC constant. So, VDC has to be kept constant, at a reference value say VDC ref. So, the VDC has to be kept constant at a reference value say VDC ref. So, we will employ a closed loop control in which we will control the front end converter, so that the DC link voltage is kept constant at VDC ref. So, we will have a scheme, a control scheme in which we will be comparing. We have VDC ref here, and what we do in this case is that we have sensors, and we can sense this VDC. So, we can sense this VDC and feed it here, and then what we have is an error, and the error is fed to a PI controller, a controller here. So, we have a voltage error, and that is fed to a controller, and the output of this controller will decide the input current. So, in this case we will have a limiter here to limit the value of the current, we can have a limiter in this case, and what we obtain is the reference current amplitude ISM, and that is converted to the reference current by a reference generator into the three references, and the references are ISA, ISB and ISC. So, these three current references are generated. Now, what are ISA, ISB and ISC? This ISA, ISB and ISC are the three currents that are drawn from the supply. So, if we have the supply, we have the supply here, and the supply is giving three currents, and the currents are in this case ISA, ISB for B phase and ISC for the C phase. So, what we are trying to do here, we are trying to generate the three reference currents ISA, ISB and ISC of the front end converter, and the front end converter will be so controlled to ensure that the actual current follows these reference values. Now, we know that the front end converter has to be controlled to ensure that the actual current ISA, ISB and ISC follow the reference values IA star, IB star and IC star respectively. So, if we try to see, the capacitor voltage has to be maintained constant. So, if we want to maintain the capacitor voltage constant, the power has to come from the source. So, if VDC has to be increased, the power flow should be in this direction. So, this is to increase VDC. It means, if we want to increase VDC, the power has to come from the source, that the voltage in the capacitor will be more, the capacitor charges up. And if the voltage goes to a very high value, we need to decrease VDC, the power flow has to be reversed. The power flow should be from the DC link back to the AC side. So, we have a reverse power flow. We can say that the P has to be reversed like this to decrease VDC. So, the power in this case should be like this to increase VDC, and the power flow should be reversed to decrease VDC. It means the capacitor has to be discharged, and if you want to discharge the value of capacitor, we need to take out the energy from the capacitor, and that can be done by controlling the front end converter. So, this is the basic principle. So, if we want to have higher and higher voltage, we need to have the current, the input current in such a way that the capacitor charges up. Now, if you want to reduce the value of the capacitor voltage, that is VDC, we can drain the capacitor through the front end converter, and hence the front end converter should have the bidirectional power capability. So, the front end converter which is this one, this is the front end converter, and this is the load end converter. So, we can say that the front end converter should have bidirectional power capability, should have bidirectional power flow capability. Now, if we see, the front end converter delivers two types of power. One power which is fed to the motor, and the second power which supplies the loss of the capacitor and the overall system. So, if we want to increase the capacitor voltage, the front end converter has to supply the demand of the induction motor plus extra power to charge up the capacitor. Now, similarly, to discharge the capacitor as to bring down the voltage, the front end converter should supply the demand of the induction motor plus the power which has to be drained from the capacitor, and hence the power flow through the front end converter has to be bidirectional. So, this is the front end converter, this flow has to be bidirectional. So, we can say that the power flow can be bidirectional here depending upon the situation, that whether we want to increase VDC or we want to decrease VDC, whether the motor is operating under motoring region or this is operating under braking region. In fact, in this case we can operate this both for motoring, we can go for motoring and as well as for braking. We can also have electric braking. For motoring, the power flow is from the converter to the motor like this, and for the braking the power flow has to reverse. So, it has to from the motor to the DC link and back to the source. So, in fact, this drive system is not only a utility friendly drive, this is also a 4 quadrant drive. We can operate in motoring, we can operate in braking, in fact, we can operate in all 4 quadrants. We can operate in forward motoring, forward braking, reverse motoring and reverse braking. So, the drive can be bidirectional, also the power flow can also be bidirectional. The drive can have forward rotation, can also have backward rotation, and the power flow can also be bidirectional. So, let us concentrate on the control of the front end converter. So, the front end converter basically maintains the voltage VDC constant. So, if we concentrate on the control of the front end converter, we can appreciate that by drawing a phasor diagram. Now, what we say here is the following, that we have the system and this is the source voltage Vs phasor. We represent the voltage by means of a phasor, and then we have a reactance, and then we have a converter which is Vc, and the current flowing through the reactance or the inductance here is Is, this is also a phasor, and the value of the reactance is omega L. So, if we replace this in per phase quantity and try to write down the phasor equation, we can say that the source is supplying two quantities, one is the reactance drop, other is the converter voltage. So, we can say here that Vs is equal to j omega L Is plus Vc. So, if we see it little in a more detailed way, so we have a system in which we are having a voltage here, that is the source voltage, and then we have a reactance, and then we have the converter voltage, and the current is coming from the source, this is Is, and this reactance is j omega L. So, this is our single line diagram, equivalent per phase equivalent circuit. We are replaced by the phasor quantities, the source voltage, the reactance drop and the converter voltage. Now, if we write down the vector equation, it is Vs is equal to j omega L into Is plus Vc. So, we can also represent this by means of a phasor diagram. So, we start with the voltage, that is the converter voltage. So, we can start with the converter voltage here, or we can start with the source voltage, that is Vs, and our objective is that the source voltage and the source current should be in phase. So, this is Is. Is and Vs are in phase, the power factor is unity. So, we can calculate Vc is equal to Vs minus j omega L Is. So, if we try to see what is j omega L Is, this is basically a lagging quantity. So, we have this quantity is minus j omega L Is, and this is 90 degree, and we can complete this vector diagram. This is a vector triangle, and the third side would be the V converter. Now, here we have fulfilled our criteria that the input power factor is unity. So, the input power factor is maintained unity because Vs and Is are in phase. So, if we can control as per this phasor diagram, we can ensure that the input current of the converter is 1. The input current which is drawn by the front end converter is 1. Now, this for the motoring condition. Motoring means power is flowing from the AC supply, that is the grid, to the DC link to the motor. What about the braking? In the braking, when we brake a motor, the motor is usually having a lot of kinetic energy. When the motor is running, it is having its own mechanical inertia, and due to the mechanical inertia, when the motor is in motion, it has got lot of kinetic energy in the form of half j omega square. And when you want to arrest the motion, when you want to brake the motor, this energy has to be fed back somewhere. And if we talk about a regenerative braking, this energy in the mechanical inertia of the motor has to be fed back to the supply, and hence the supply is not giving power, is receiving power, and that means the power factor is minus 1. So, this is for the motoring. Where the power factor is 1, it means Vs and Is are in phase, and for the braking condition, we have the voltage is Vs here and the current is out of phase in this case. So, here theta is 0, theta is the power factor angle, that is equal to 0 in this case. Now, here theta is 180. Now, in the first case, in the motoring case, we have power factor is equal to cos of theta, that is equal to 1, and for the braking case we have power factor is equal to cos of theta, that is equal to minus 1, which means power is fed back to the supply. Now, if we draw the phasor diagram for the braking situation, we will have the following phasor diagram. We have to find out what is minus j omega L Is. So, this is Is. Now, negative of this is lagging behind this. So, this is minus. So, this is minus j omega L Is, and if we complete this vector triangle, the third side will be the converter voltage. Here we can see that the converter voltage is leading this by an angle. So, it means the converter is supplying to the source. If you compare this with the motoring case, in the motoring case the source was supplying the converter like a synchronous machine. Now, when the source is supplying the converter voltage V c lags behind the source. So, this is basically the lagging angle. We can say this something like a power angle delta, and delta is negative here and here the delta is positive. So, in this case we find that the power flow can be reversible. For the motoring the power factor is +1 and for the braking the power factor is -1. So, if we think about a closed loop control, primarily we will be talking about the control of the front end converter. The front end converter is the one which maintains the power factor unity, and hence it ensures a utility friendly drive system. Now, if we talk about the control of the front end converter, we have to control the current in the converter. The converter is operated in PWM mode and the current is controlled in such a way that the power factor is unity. So, we will discuss about the control of the front end converter. First of all, it is a PWM converter, which means current input current is sinusoidal. Close to sinusoidal. So, what we do here is that we want to maintain the DC link voltage constant. So, we start with a DC link reference, that is VDC reference, and we compare that with the actual VDC, and then we have a PI controller which is followed by a limiter, and then we generate the peak value of the current sin Sm. This we multiply with omega Ls, the reactance, and then for one phase, if we talk about only phase A, we multiply this with sin omega t plus pi by 2 and then we have the voltage from the source V m sin omega t, and we generate the I phase reference VCA reference. Now, this is basically for phase A. Now, phase B lags behind A by 2 pi by 3. So, if we talk about phase B, the phase B situation will be lagging behind this by 2 pi by 3. So, to show that how phase B will be implemented here, we have a similar structure in this case, a multiplier. Now, here what we do, we multiply sin omega t plus pi by 3 pi by 2 minus 2 pi by 3. And then we have the voltage in this case V m sin omega t minus 2 pi by 3, and what we obtain here is V c b reference. Now, similarly for C phase, if we implement for phase C, we have again another multiplier. In fact, these voltages are V s a n and this is V s b n source voltages, and similarly we have the phase C, we multiply with sin omega t plus pi by 2 plus 2 pi by 3 phase shift, and then we have this voltage V s c n is equal to V m sin omega t plus 2 pi by 3, and what you obtain here is V c c star. Now, these are the equation that we are implementing from the phasor diagram. From the vector equation, we are converting the corresponding equation into the time domain, and we are generating the reference signals for phase A, phase B and phase C voltages of the front end converter. Once the voltages are known, V C A star, V C B star and V C C star, we can feed this to the modulation block to generate the modulating signals and the drive signals for the front end converter. So, this is how we can control a utility friendly drive, in which the input current is sinusoidal because the converter is a PWM converter, and we are ensuring that the input power factor is unity. So, we are only drawing active power from the source. In the next lecture, we will be discussing more about this and also see some topology of high power drives and how we can implement utility friendly configuration in high power drive systems.